Okay, class, let's talk about Chapter 8, right triangles.
Yay!
Woo!
Hey guys, let's talk about section 8.1.
Oh, yeah.
Similarity in right triangles. What up? Okay, let's review the geometric mean. X is the geometric mean between A and B when A over X equals X over B. This only applies if A and B are positive numbers. Let's find X. So A over X equals X over B. So to find X, you have to cross multiply, making it X squared equals AB. Then you simplify by finding the square root of X. X equals rad AB. And this is your geometric mean. Let's try another example. Find the geometric mean between 8 and 2. So it's 8 over X equals X over 2. Cross multiply, making it X squared equals 16. Find the square root of X. X equals 4. And 4 is your geometric mean. Easy enough?
Yes!
Great.
Yeah.
Let's move on to theorem 8.1. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. This means that triangle ACB is similar to triangle ANC, which is also similar to triangle CNB, making all three triangles similar to each other. There are two corollaries to this.
She can't pronounce it either, just like me.
Corollary 1. When the altitude is drawn to the hypotenuse of a right triangle, the length of the altitude is the geometric mean between the segments of the hypotenuse. Okay, this means that the altitude CN is the geometric mean between AN and BN. So yeah, that was corollary 1 of theorem 8.1. Let's move on to corollary 2. Alright. Corollary 2. When the altitude is drawn to the hypotenuse of a right triangle, each leg is a geometric mean between the hypotenuse and the segment of the hypotenuse that is adjacent to that leg. This means that AC is the geometric mean between AB and AN. Or you could use CB as the geometric mean of AB and BN. Get it?
Yes, we do. Yay!
Now let's go on to 8.2, the Pythagorean theorem. The Pythagorean theorem states a squared plus b squared equals c squared. And in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs. Let's do an example. 3 is A, 7 is B, and x is your c. So x squared equals 7 squared plus 3 squared, which is x squared equals 49 plus 9, and 49 plus 9 equals 58. Therefore, you have to find the square root of x, which is then rad 58.
Okay, guys, let's talk about section 8.3, the converse of the Pythagorean theorem. Theorem 8.3 states, if the square of one side of a triangle is equal to the sum of the squares of the other two sides, then the triangle is a right triangle. In this diagram, it states that triangle ABC equals c squared equals a squared plus b squared. Common right triangles include 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. Theorem 8.4 states, if c squared is less than a squared plus b squared, then triangle ABC is acute, like this triangle right here. Now, theorem 8.5 states that if c squared is greater than a squared plus b squared, then triangle ABC is obtuse, like this triangle right here. Now let's see if the 11, 11, 15 triangle is acute or obtuse. First, you square the 15 and both of the 11s to get 225 and a pair of 121s. Then you add the 121s to get 242. And as you can see here, 225 is less than 242. So by the theorem 8.4, 11, 11, 15 triangle is a cube.
Alright guys, let's talk about theorem lesson 8.4, special right triangles. In theorem 8.6, it states that in a 45-45 90-degree triangle, the hypotenuse is rad 2 times as long as a leg. We can prove this. Since this leg and this leg are the same length, they will both be represented by a. Using the Pythagorean theorem, we can see that a squared plus a squared equals c squared. We can simplify this to 2a squared equals c squared. Then we can simplify by finding the square root of both. Rad 2a squared equals c squared. Rad 2 times rad a squared equals c. A rad 2 equals c. Yay, we proved theorem 8.6.
Finally.
In theorem 8.7, it states, in a 30, 60, 90-degree triangle, the hypotenuse is twice as long as the shorter leg, and the longer leg is rad 3 times as long as the shorter leg. And the fun part is to prove it, right?
Yeah.
We can prove this using the Pythagorean theorem. Since this 30, 60, 90 triangle is just half of a 60, 60, 60 triangle, also known as the equilateral, the hypotenuse is 2a. Now, using the Pythagorean theorem, we can see that 2a squared equals a squared plus b squared. That simplifies to 4a squared equals a squared plus b squared. Then it turns in, now minus a squared from both sides, and it's 3a squared equals b squared. And using the square root of both, we see that rad 3a squared equals rad b squared. Rad 3 times rad a squared equals b. And rad 3 equals b. Yay!
Alright class, let's go on to chapter 8.5, the tangent ratio. The tangent ratio is the opposite over adjacent leg. As you can see in this triangle, the tangent of angle A is the leg opposite over the leg adjacent, as you can see from right here. Now that you know this, let's try an example out. So, let's try to find the tangent of x first. So, first you have to find the leg opposite and the leg adjacent. So the leg opposite of tangent x is 12, and the leg adjacent to tangent x is 5. So, for your answer, you should get 12 over 5. Now let's try to find the tangent of y. The opposite leg of tangent y should be 5 is 12. So your answer should be 5 over 12.
Yay!
Now here's a fun fact. In similar triangles, the tangent of the two angles are congruent. Yes. And by definition of tangent ratio. Now let's try this example out. So let's try to find the tangent of 56 degrees. Now here's another fact. The tangent is really based on the angle measure. So the tangent should be opposite over adjacent. So it should be y over 32. Yes. And now y equals 32 times tangent of 56 because you multiply by y, and yeah, you know how to do the math. And the tangent of 56 is 1.4826 approximately, so y is approximately 32 times 1.4826. You can find that number from the table of trigonometry, yeah. And y is approximately 47.4432, or you could just round it and get 474. 47.4. Now, yeah. Now we were able to find the measure of that tangent by using this table. This table could be used to find the tangent, and the angle measures are right here and the tangent's right here. Alright class, let's get on to chapter 8.6, the sine and cosine ratio. So the sine ratio is the leg opposite over the hypotenuse. So to find the sine of angle A, you need to find the opposite leg over the hypotenuse, which is equal to sine of angle A. For cosine of angle A, you need to find the leg adjacent to angle A over the hypotenuse. The leg adjacent to angle A is this one right here. So the cosine of angle A is equal to the adjacent leg over the hypotenuse right there. Now, here's an easy way to memorize this. So, ka, toa. Sine equals opposite over hypotenuse. Ka is cosine equals to adjacent over hypotenuse. Toa, tan, is equal to opposite over adjacent. This is very similar to the tangent. And you can also use the table of trigonometric ratio for this too.
Okay, now let's talk about lesson 8.7, applications of right triangle trigonometry.
Yeah, man.
Think of a spectator on the top deck of Dodger Stadium looking down on the field, making a 30-degree angle with a horizontal line, as you can see here. The angle between the horizontal line and the line of sight is called the angle of depression, right here. Meanwhile, the Dodgers catcher must look 30 degrees above the horizontal line to see the spectator, right here. This is an angle of elevation. We can use these angles to find how far an object is from another or how tall an object is. For example, if the stadium is 250 feet tall, we can use the equations tangent 30 degrees equals 250 over x, and tangent 60 degrees equals x over 250, with x being how far home plate is from the bleachers where the spectator is sitting. Try solving these equations. The answers are about 432.98 and 433.03 feet. Note that the tangent values are approximations, so you get two different answers. But overall, a better answer would be home plate is around 430 feet from the spectator.